Now we're going to change gears a little bit and talk about electron pair geometry. Okay, so the purpose of these sets of videos is we're going to start talking about the shapes of molecules. And molecules really have three-dimensional shapes. So far, we've just looked at Lewis structures. And the purpose of Lewis structures is only to show how atoms are connected. So in this case, for methane, CH4, this carbon is bonded to the different hydrogens. Those lines are showing connections. Also importantly, it shows that the hydrogens are not connected with each other. But importantly, this is not what the shape of methane is. You can draw the Lewis structure any which way you want. Right here, it is drawn as a cross because it kind of makes sense. That is not what a real methane molecule looks like. Instead, a methane molecule looks like this, where you have the carbon atom in the middle, that's the black sphere, and then the white spheres are the hydrogens. And so there's a three-dimensional arrangement of these atoms in space. So they are, kind of a depth to it. It's not just a two-dimensional projection. Lewis structures are not meant to show shapes. They're only meant to show connections. Where are the bonds? Real structures like this is a three-dimensional rendering that's showing the real shape of a molecule. If we want to draw Lewis structures in such a way that we imply shapes, we can use these special lines. And so the special lines we're going to use is one, we'll use what we call dashes. So that's this one going here, right? So the idea here is these dashes are showing that this bond is going into the page, it's going away from us. And then we also have these wedges. The thick wedge is coming here. This hydrogen is coming out at us. So this Lewis structure is showing the same 3D shape as this 3D motion or 3D rendering up here, right? We can see two of the hydrogens, the one that goes up and to the left, are in the same plane of the screen. Then there's one going back and one coming out towards us. So these are the different ways that we can represent and render these different molecules. Again, that thick wedge means it's coming out at you, and the dashes mean it's going away from you. And importantly, when we draw molecules like that, straight lines are just in the plane of the page. So that would be considered flat. Okay, so within this realm of molecular shapes, we have two different types of classifications. We have electron pair geometry, which is the relative position of bonds and lone pairs around one atom. And then we have molecular shape, which is the arrangement of all atoms in a molecule. So these are related ideas, but are slightly different. So electron pair geometry, that is something that is every single atom in every single molecule has. It's the description of what is the arrangement of things around that one atom. Molecular shape then describes all of the atoms in one molecule. Okay, so this would be a characterization that we have for, this molecule has one shape. All the atoms within that molecule can have different electron pair geometries, but the whole molecule only has a single shape. You'll also notice one of the important differences is that molecular shape is only concerned with atoms in a molecule, whereas electron pair geometry is the relative positions of bonds and lone pairs. So molecular shapes don't care about lone pairs, only what are the relative positions for all atoms. When we're talking about molecular shapes, when you start to get into bigger molecules, the shapes will become really complicated, and it's not really common to describe the shape. That's why we use the electron geometries. So instead, these molecular shapes are really only going to be defined for compounds with one central atom and then multiple outer atoms. So those are the kinds of molecules that we have our procedure to draw Lewis structures for. So let's take a look at using this classification. So I got two molecules represented here, C6H12O6 on the left, that's glucose, and then CHCl3 on the right. So C6H12O6, we can see this is quite a complicated molecule that I'm looking at here. There's a lot of atoms going in a lot of different directions. There is no defined shape for all of these atoms. Basically this overall shape is so complicated, no other molecule would have this, and we would just call it like the glucose shape, right? And so that's not really useful in terms of a naming convention because it doesn't really help us. We can't describe anything else. That's not really worth coming up with a name. But if we look at all the atoms in the molecules, we can see that each individual atom, say like this carbon atom right here, has a particular arrangement of the other atoms around it. And that is the electron pair geometry. And so we can count them out. We can look at all these carbon atoms. We can see that those carbon atoms have other atoms. They're kind of forming the backbone, and they have the other atoms arranged around them. And so that's going to give us a lot of information as to the relative positions of all the different atoms in the molecule. CHCl3 on the right, then, we can see is much smaller. It just has a central carbon atom and then 4 outer atoms. So what that means is that this molecule has a defined shape. We don't just call this the Cl3 shape. We can name what this shape is. And we'll learn how to do that, but because other molecules that are small are going to mimic this same pattern. At the same time, you still do have a defined electron pair geometry. Remember, every single atom and every single molecule has one. So just because there's a shape doesn't mean we don't talk about the electron pair geometry. So where do these shapes come from? The shapes are described by what's called valence shell electron pair repulsion. It's pronounced VESPR. I know that swaps the E and the S, but we call it VESPR. And the idea of VESPR is that electron groups arrange around atoms to be as far apart as possible. We can understand that based on the idea that, electrons are all negative, right? They're all negatively charged, and negative charges repel each other. So if you have an atom that has lone pairs, bonds, whatever, all these electron groups around that atom, they're going to try to stay as far away from each other as possible. Okay, and so they're going to arrange in such a way. And so what that means is if these bonds and stuff just arrange to be far apart from each other, the only thing that matters as far as determining what these different geometries are going to be, the determining factor is going to be the number of electron groups. Because if you're trying to spread out, you're always going to get the same answer for a given number of electron groups. Here we can see what the associated shapes would be based off the different numbers. We're really only going to be focusing on smaller molecules. So our possibilities are we have 2 electron groups, 3 electron groups, or 4 electron groups. And the corresponding shapes are linear, trigonal planar, and tetrahedral. And again, it's all about pointing as far away from each other as possible. So if you have 2 electron groups, one will point in one direction and one points the opposite direction. And we can see that orientation is shown or displayed by what we call the bond angle, or the angles that we have here. In this case, it's the 180 degrees that corresponds to that sort of straight line. Then if we go up to 3 groups, again, they spread out. We get what's called trigonal planar. So trigonal meaning you have 3, planar means they're all flat. So this is still a 2-dimensional representation, and you're now 120 degrees. They have to get closer together because you have more groups. Once you step up to 4 groups, that's where you enter 3 dimensions, and you now have the tetrahedral electron pair geometry. And so that will spread out. It's 109.5. Again, it's a little bit closer. But you can see we've now moved into 3 dimensions. Here are representations of the same thing using balloons, right? It's the same idea as what's going on with electrons, right? These balloons take up some space. They want to stay as far apart from each other as possible. And so we can see we get this nice linear representation or the trigonal planar. And you can see they're flat against the table that they're on. So you can see it's still, that's the idea of the planar. And then once we go to 4, that's where we start to go. We have the 1, 2, 3 that are kind of pointing down, and then the 1 up in the 3rd dimension, right? So this tetrahedral shape is now going up. It can't be flat anymore to be maximally spread out. All right, so we know that what really matters is counting groups. And so what we want to do in order to figure this out is figure out ways of how to count these electron groups. And really what we're looking at is just how many directions do electrons stick out from the central atom. So if I look on the left here, I have CH2O. I've got the Lewis structure given for me. And I want to count as electron groups. So I know I have, say, a bond here, a bond here. And then my 3rd bond is a double bond. So this can be sometimes confusing because it's called electron pair geometry, but this double bond it still just counts as one group. Both of those electron pairs are bonded to the same oxygen atom, so they have to point in the same direction, right? They have to point towards that oxygen atom. And so we just count both of those electron pairs as one group. So a double bond, single bond, triple bond, doesn't matter. Each bond is a group. So we can see that in this case, this molecule, there are 3 electron groups attached to that carbon atom. And so we have a trigonal planar electron pair geometry. This is now a 3-dimensional representation of the molecule. Again, you'll see it's flat. It's that planar, and then the trigonal is the fact that the outer atoms form a triangle, and it's a flat triangle. If we now move to talk about the NH3, we can count 1, 2, 3 bonds. So those are those 3 atoms that the nitrogen is bonded to, and then there's also the lone pair. Those lone pairs of electrons still take up space, and they fill part of the kind of the shape or the arrangement of the electron groups. And so we can see that for this ammonia molecule, the nitrogen ends up taking a tetrahedral electron pair geometry. That lone pair, that unshared electron pair, fills up space around the nitrogen. And one of the ways you can think about it is if we only had, say, the 3 bonds, they can't point, if they're pointing out trigonal planar, they get pushed down by this lone pair, right? And that's why they all then move to pointing down, like we see in the tetrahedral orientation. So the underlying goal, or the underlying mechanism of how we diagnose shapes and all that stuff, is take our Lewis structure and count electron groups. The number of electron groups is always going to be exactly equal to the number of lone pairs plus the number of outer atoms. Participation 626, question 1. How many electron groups are attached to the central atom in each of the following molecules? I have H2O and NO3. This is the first question on participation 626 due Friday, June 26 at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many electron groups are attached to the central atom in each of the following molecules? I've got a water molecule and a nitrate molecule. How many electron groups on the central atom of each of those? All right, so let's look at some examples then of determining electron pair geometry. I have CO2 on the left and ASH3 on the right. We're just going to start from Lewis structures. One of the things to note, the first thing is always going to be determine Lewis structures. So if you were given a formula, and you take that formula, turn it into a Lewis structure. Here I have Lewis structures, so we're going to start from that. Okay, so CO2, I want to determine the electron pair geometry. The first step is going to be determine the number of electron groups. That's going to be number of outer atoms plus number of lone pairs, one group, one group. That means this molecule has 2 groups, which means it is a linear electron pair geometry around that carbon atom, and the bond angle is 180 degrees. Once you know it's linear, that just directly translates into 180 degrees. Those 2 terms, calling it linear or 180 degree bond angles, mean the same thing. We can look at the actual 3D representation of this molecule. It's called linear because the atoms are in a straight line, right? The whole molecule, the 3 atoms are in a straight line. So then ASH3 on the right, if we want to count groups on that, I've got the atoms, outer atoms, I'm going to count those, 1, 2, 3, and then I count that lone pair. There are 4 groups. That means this has a tetrahedral electron pair geometry around that central atom, and the bond angles are necessarily 109.5. So tetrahedral always means 109.5 degree bond angles. And here's my representation of the molecule. So again, that angle, that 109.5, that's describing, that's not very clear, that's describing this angle right there. You take 3 of the atoms and you're describing that angle. Similarly, you'd have the same angle on that side and then also between the back ones. So all of those angles are 109.5. Okay, so those are smaller molecules where we only have one central atom. But when we're talking about these electron pair geometries, we can also get insight on any atom in any molecule. So here's vitamin A. It's a pretty big molecule, but we can start to see if we can parse out some information as to what the whole molecule kind of looks like based on what the arrangement around each of the atoms is that are in the molecule. So when it comes down to looking at bond angles, that's all about arrangement, which is all about the number of electron groups. How many bonds does it have? How many lone pairs does it have? I got a lot of carbon atoms here. And so as a result, that's really just counting bonds. So, there's 4 things that it's bonded to, 4 different atoms that it's bonded to. That's tetrahedral, and it'd have 109.5. If there was 3 things, it'd be trigonal planar, and their bond angles would be 120. So if I take a look, these carbons kind of hanging off the side, they have their connection and then 3 hydrogens. So that's 4 things. So that'd be tetrahedral. And I can see that, the carbon next to it has that. And in fact, this one in the middle, then that's a carbon that's only bonded to 4 carbons. So that would be tetrahedral. And that's going to kind of continue around that ring. Okay, and those are all bonded to 4 things. And then, all the other decorations kind of hanging off the side. All those carbons are bonded to 3 hydrogens kind of hanging off the side. So those would all be tetrahedral, have that spread, that 3-dimensional spread with that 109.5 degree angle. And there's one other carbon that I can see in the chain. It's bonded to 2 things, and it's bonded to 2 hydrogens, and oxygen also with its 2 lone pairs, and then the 2 bonds. That oxygen is also trigonal planar. So I got everything. I can find trigonal planar. So if I return to the rest of these carbon atoms, I can see that all the other ones that aren't circled, all have a double bond. So like I look here, it has 1 double bond to a carbon and then 2 single bonds. So that gives it 3 total atoms it's bonded to, corresponding to a trigonal planar geometry. And that's true of the carbon that's on the other side of the double bond, and that's true of all the other carbon atoms in this chain. So if I overall kind of look at this molecule, I can parse out that basically all the carbons hanging off the side and most of that ring that I kind of had were all tetrahedral. And then I have this line of trigonal planar atoms, right? And each of those atoms has bond angles of 120 degrees and importantly is trigonal planar. So if I take that information, I can then look at an actual depiction of a vitamin A molecule. And if I look at all the different parts of this molecule that were represented, I can see, the carbons that were hanging off the side, right? Those all had that 3-dimensional tetrahedral 109. I can see there's kind of a bloom of hydrogens. And I can see also that the carbons that wrapped around this side of the ring also were tetrahedral. And as a result of that tetrahedral nature, they have that 3-dimensional spread. There's those hydrogens. And I can also see one of the things is that if I look into this ring, it's going up and down and up and down, and it's jagged, right? It's bumpy because they have 109 degree angles. They're kind of moving up and down. There's that 3-dimensional nature to it. Whereas if I look at along here, where I had all of my trigonal planar carbon atoms, I can see that all of them have that nice 120 degree spread. They also are all in the same plane. This part of the molecule is flat, right? There's no up and down nature to it. And so I can start to see this sort of, that idea of these, individual atoms, the orientation of atoms around that, the bonds around those atoms imparts overall shape to the molecule, right? And so what ends up happening with vitamin A is this flat part over here functions as like a big paddle, right? Because it's flat. And so it can move overall it can get shifted to go kind of flop up or it can flop down. And so it's kind of a switch where it can move as this long flat paddle sticking out sideways, or does it move down? All sorts of different orientations like that. And that's how vitamin A functions. It goes up and then it flops down, but it's a big, rigid, flat paddle. And so that trigonal planar arrangement imparts that aspect around it. Participation 626, question 2. Give the bond angles around each indicated carbon atom. There's 2 carbon atoms in the left molecule and then 3, 4, 5 on the right molecule. This is the second question on participation 626 due Friday, June 26th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, give the bond angles around each indicated carbon atom. 1, 2, 3, 4, 5. Okay, first video done. 2 participation questions in this one. Participation 626 is due Friday night. Gotta watch the rest of the videos to find more. And then after that, module 8 homework is gonna be due on Saturday over on Blackboard, or Active. We don't have any post-lab or anything because you did the lab practical. Do want to note that next week, we're gonna have more videos, some lab assignments, homework, that kind of stuff, but also importantly, the lab technique presentation videos are due Wednesday, and then either Tuesday, Thursday on campus if you chose the in-person presentation, and our final exam will be Thursday. Class ends next week. The 2nd is the end of the class. If you have any questions about anything, let me know. Otherwise, we are getting started. This will be the end of chapter 7 through this set of videos. I'll see you in the next one.